So, good afternoon. Let us start my talk on the CNN, convolutional neural networks, LSTM, long short-term memory networks, then hybrid CNN-LSTMs, encoders, and GAN. So, in the previous lectures, you have got the basic theory of CNN. So, I will not go into the details, rather I will cover these things, some of the examples of this, my work of CNN and hybrid CNN-LSTM in a particular problems of gravity of Northeast India. So you have this, the systematic development of this AI and machine learnings, and then coming the deep learning in previous lectures, and there are as many number of deep learning models are coming up, and they have been used variously in the different domain of art science. I got some examples of the applications of the CNNs and the varieties of the CNNs to the different problem of the seismic and the seismological inversions. So here we will mostly cover that some brief outlook of these methods very quickly, and then directly we'll move to that applications part. So in these lectures, the popularity of CNN already has been established in our art sciences. So mostly it operations wise it is convolutional based, and the deep learning coming into the pictures, this is two ways. One is that either you can add these neural networks in a multiple layers, and that will also form a one form of your deep learnings. But there are some special architectures like convolutional neural networks, long short-term memory networks, and hybrid. They are actually special type of networks. Not only the number of the layers there is more, operation-wise also more, and they actually have some special structures. And that is one of the contrasting features in the deep learning literature. And as you know that there are two types of problems we solve in our art science. One is that either this data can be a geospatial data or it is a time series data. And we invert the data to derive many models parameters according to the problems you are solving. And particularly in the geospatial data and the image data, there is a advantage of using the CNN type of network, and that is the operation wise that the convolution is one factor, and second thing is that it actually extract the features from the image, and that will be very useful for deploying any job like classifications type of jobs. Because in art science invariably we solve these two types of problem, either it is a regression problems or it is a classification problem. And if you do these things in between, there is a problems we call the probabilistic, or the in terms of probability, we predict some variables of your art variables in terms of probability. It is not that some value, it is a that any event whether it will be occur no, the likely. So it is a value of the probability, not it is the value of just that some numerical value or something like that. So that is the three things we have, and there is a structure called the recurrent neural network. So that recurrent neural networks, it is very popular was in the time series forecasting problems where your subsequent interpretations, so subsequent layer processing is dependent on the previous layer information in terms of your time series forecasting problems. So any time series forecasting problems, we need to have the relations between your present state of information with the previous state of information. Then only we can have some relationship or the models which can map that the previous value of your time series to the present value and the subsequent. So here the problems start in the time series problem, that when you are going for the long range prediction, long step, one step, two step, three step, or multi-step predictions, at the time these predictive models fails to capture the predicting accuracy what we are looking for. So that is associated with say there is a problem, prominent problem, vanishing gradient problems. Mostly we have that the time series forecasting problems. We have the previous time series data we apply to the your networks. It predict that output. So during the learning or the training, cost function evaluation was there. That cost function evaluation either gradient or derivative based. Now once it is ahead, say with the predictions, then there is a problem with the gradient information that loses the information which contains in the problems itself. So that gives you the disadvantage of the problems faced in the, say, for example, recurrent neural network. So in order to overcome this, a special type of time series predictive predictions models came that we call the short long-term memory predictions, where there is a chances that we can control that what type of information we can store it, what type of information we can forget it, and that things actually very beautifully handle in the type of network called the LSTM. And that usually any predictions models, once it is developed, then it may be very good for your short-term predictions. But with this training data set, it may fail for your long-term predictions problem, to solve this long-term prediction problem. Now, other way, if you develop that time series forecasting problem, particularly for the long type predictions, then they cannot able to produce a very good predictive accuracy in the short term. So both the things cannot go in hand in the recurrent neural network problem. So LSTM, it has the flexibility of the both the things can handle simultaneously. The what type of information you want to keep, what type of information we want to forget, and what type of information it should be processed through this LSTM network. That is the advantage of LSTM. And this CNN LSTM, it is a hybrid where the advantage of this CNN as well as the advantage of the LSTM both can be exploited with this hybrid type of network. Then autoencoders, as it is largely used for your denoising purposes, but you have already exposed that it may be invented or had been novel way it can be used in the different problem or a seismic. So basically it is a some type of networks which has been very similar to works in a problems like dimension reduction, denoise, reconstructing that, say, noisy data to the denoisy data to the noise-free data, something like that. And then GAN, say, generative adversarial networks. So it is a networks which actually does that, the new things, means how we can hypothesize that data, or how we can generate that data providing some hypothesis. And that GANs networks allows that, say, if there is a noisy data, so there is a denoised data, how we can simultaneously be given to the networks so that this network can learn that which one is the noisy, which one is the noise free, or if any image is a fake or if it is real. Both the things can be done, could be provided during the learning stage. So this will give you some advantage. That type of networks is very robust in the sense. Robust means, robustness is a property, it is statistical property we call it, that any models which is indifferent to the outliers present in the data. Usually you define outliers, it is uncontrolled error in your data systems. Now any problems or any methods we call it is a robustness, it is not the correct way to define. Robustness is a algorithms or any models. If it is a tested that if the outliers is present in that case, even this particular algorithms performs good, means it is not very disturbed by the noise presence in the data or outlier type of noise presence in the data. In that case, we call it is a robust one. So robustness is a property which is prominent in the GAN, because at the same time we are providing the noisy data as well as the noise-free data during the training itself. So that networks naturally is learning that which one is the real, which one is the fake, which one is the noisy, which one is the noise-free data. And that gives its advantage about the robustness, that in a real world, we may expect that some amount of the noise which is very adverse, not exposed to that particular network before the training or like that. In that cases, this networks provides a very excellent.
Sounds like these networks, they do complement each other. So under what circumstances do that context of probabilistic or actual numerical value comes into picture to select any of the networks?
So can you repeat the question, please?
The way it sounds is like these networks, they do complement each other. They do help each other in one way or the other. Now the question is, under what circumstances the probabilistic or the actual numerical value comes into picture so as to select the network that has to be deployed?
So here we have discussed about 1, 2, 3, 4, 5 types of networks. Okay. We are performing differently.
So in case by case, if you say, if you are analyzing a gridded data, let us say, or the image type of data, in that case, this your CNN can be a very effective models to handle this, right? Now I am talking to the second one, say long short-term memory network. It is a very good for the text to image or something like that, but in the numerical value analysis, say, in that case, time series data, particularly time series forecasting problems. So let us say you have your data of previous 100 years, some records. We want to develop some time series model to forecast some Earth's variable in advance, say 1 step ahead, 2 step ahead, say 1 month ahead, 1 month ahead, 1 year ahead, or 5 years ahead, like that. So the time series problem, this second models sounds good. But the fact that if you want to handle this both the things, say your geospatial data, which is spatial, but it is also a time varying field you want to capture. So in that case, this combined, say hybrid networks, CNN-LSTM can be a handy tool to overcome the problem. But the fourth one, the autoencoder, it has a large number of applications you have seen. It can denoise it, and it performs in a ways that their input and the target is the same. In the most famous way, this in autoencoder, this input and the target is the same, but it is not the same with the other networks. Okay, but the last one is the GAN. GAN is one philosophy where any type of networks can be used. Okay, but the thing is that when we are providing this training data, so that data, it is provided this which one is the noise-free data, or which is the pure data, which is the impure data, let us say. So the adversarial complexity, whatever you want to think or what you are assuming, both the things actually providing that networks simultaneously. So it will, during the training stage itself, it is actually learning that which one is the good, which one is the bad, and that way that it is actually giving some advantage that if your real data, it is just a noisy or there is a suffered by some outliers, that in that cases, this last one, say GAN, will give you that stable results. It will not adversely give the poor results or something like that. So in terms of robustness, it is actually gives the better result in in compared to the other models.
Training data. Suppose if 90% of the training data was noisy and 10% was free from noise, then it can consider that the data which was free from noise can be as a noise.
So these type of things are there because if you do practically, then only it will be understood that which part of things can be dominated by the others. Because some of the examples Professor Sen's discussed about that when we are stopping and that where to stop that so that it should not learn the noise part. So that is one example he was discussing in the first half, that we have the data which is noise free, we have a target which is noisy. But when you are starting from the mapping from noise to say noisy, there that early stopping technique has been used so that the networks not getting into the part that the noisy or something like that. So in that case, again, the overfitting is a one issue, which is actually, it is there, inherently there. That has to be addressed by the way we have learned it, or by using this different type of techniques. They are all, that is a research problems where we can see that, because many of our machine learning literatures, what happens that theoretically we understand it, but many of the theory actually not foolproof. It is because it inherited many of our properties which is based on the data. And how you are creating the data or how you are attacking that problems, that also gives you some of the results, what personally I feel. Abhishek, are you saying something?
In context of prediction, we usually hear three terms like the prediction is accurate, it is reliable, and it is robust. So could you please differentiate between these three terms? And also, like, if our prediction is accurate, it should be reliable also. And if a network is able to give a correct prediction, it means it has gone through a robust training. So could you please differentiate between these three terms?
So it's a good question.
Because when you are predicting anything, so we need to answer the things that whether your model is accurate. So accuracy is one part. Second part is that how it is robust in terms of stability. So accuracy, as we say that, how we will say that this model is very accurate. Usually we address this issue to see that, say, once this network is trained, validated, tested, once it is done for the real world data analysis, we apply to the new data and see how our predictions is like that. But for the new data analysis, you don't have the answer what should be like that. So now what we did that some part of your data we kept that which is untouched, we call this a test data. There we apply that different type of statistical parameters which is actually good, say mean square error, mean absolute error, say R square R. So I have said that they have their different, this type of statistical, the statistical performance, they act differently. Suppose your output is perturbed by outliers. So in that case, it will not affect that, it will not affect that mean absolute error, say MAE, not much, rather than R square or mean square error. So this is because this MAE, this mean absolute error, it is comes from based on the L1 norm, which is actually says that it is indifferent to the outliers present in the data. So in that case, it is a more stable. So MAE will be more stable indicator in case it is your data is perturbed by outlier. But if the data is perturbed by say outlier like then L2 norms may give you some adverse things. That is a number one. And second thing is like that you want to use these things. But that is the whole theory is that this your predictions accuracy we are concentrating only the how the data is noisy or no. But when you are address these things that okay, our models predicts good, but we also see that how it actually see that complexity of the problem. So usually we see this that our predictive model should be accurate as well as it also should explain that if the adversity, other adversity is there, that also it should be addressed moderately. So there is a complexity we can express in two terms. One is the complexity due to the predictions data predictions where the data is not part of, not pure, say noisy. There is one component, and second component is the model complexity, the how your underlying mapping or model is smooth. So these two things has to be actually see one in the same time. And the third is that the robustness. The robustness is that if your data is accurate, your predictions model is very accurate for the noisy data, but it may fail adversely in the presence of outliers or any other unknown noise, which is actually not statistically known. So in that cases, my suggestion is that we need to compromise between the both. Means you need to see also pay attention to the accuracy, as well as we need to see that how your algorithm is good in terms of your different level of noise you are expecting, and see that how it is stable in presence of the noise which has been simulated by you. So we need to test both the things at the same time. Then only we can see that, but both the things cannot be the same, because your models may be accurate in that your explain the data complexity part, but it may not give that much of accuracy in the model complexity part. That is why we need to trade off, or we need to take a call that in which side you want to pay more attention to that. And that is another way we will see that in the interpretable AI, these things can be beautifully explained, that what type of things and how they are explained to your predictions. Okay, so this is a convolutions operations which is discussed, that this convolutions operation is the main essence in your convolutional networks, and that actually extracts some features, and that features will be used for your CNN training to map the models. This is one example. Now this is a structures you have that inputs, there is additional structures, say pooling, which extract the informations. Then there is a convolutional layers, and there is a fully connected layers and the output layer. So if you match one-to-one to the standard neural networks, say multi-layer perceptron models with the CNN, that your input layer is same, output layer is also the same, only in between the hidden layers, there many things are actually there, which is operation-wise actually extracted. So the layer by layer, you are extracting the features, and these features, again, you are summing it, you are flattening it, all these operations are the matching with the dimensions, and the last two layers also similar to your layer, which is already defined with the MLP. So here the difference is that filter we have used, because convolution itself is a filtering theory. That is why we use this filter. We define the filter in our coding. So filter, number of the filter is equivalent to the number of the nodes usually, or number of the processors you taken into account with your networks. Whether the output layers, which is a fully connected, it is a dense layer. So it is a layer similar to the output layers we consider your MLP. And the pre-processing, let us say, what we did in the conventional neural networks, like we normalize it. Then if the noise presence is there, we apply some of the transformations to remove that noise in the pre-processing step. And then this noise-free data we apply in the process and train that networks in the conventional. So these type of things are naturally taken in a one frame, the CNN, where these convolution operations will take care that the filtering part, and the second part is that this all operations like pooling and different type of operations is the added features. So it has, so in a case of your CNN, it can be used for your 1D, 2D and 3D problems. And let us take an examples of your 1D, where we have used some examples that we have used these CNN-LSTMs and CNN-LSTM in a framework called that. Suppose let us say examples of your geophysical problems that you have given a geospatial coordinates, say latitude, longitude, and the gravity anomaly of your particular area. We want to predict some depth of your geological interface. So how we can formulate it? So before going to that, the second networks we will discuss. Second is the long short-term memory networks. As you see, this is the basic structures here, that there is inputs and there is output layer, and in between the LSTM cell is there. In under this LSTM cell, there is operations are there. This type of operation is says that this inputs it will takes, and there is a units called the gate, say input gate, hidden gate, output gate. So the amount of the information which is taken into this LSTM, and this will allow you that what type of information you want to keep presently and what type of information you want to forget it. Because what is happening that our memory management can be better way done in the LSTM network. So let us say we want to keep our information related to the short-term predictions, or you want to keep the information related to a long-term prediction, or in between. So this type of flexibility is there in your LSTM cell, where you see that there is a H hidden state which is denoted by subscript T-1. This is the HT. That means there is a relation that what is the present state of informations, that things has been taken in a two-way, in a time series problems. One is that CT-1, another is the CT. So this way that the previous state of informations and the present state of informations has some relations when it is actually processing that cell. And this way it has the flexibility that what type of information is immediately required, we can keep it. What type of information it is not immediately required, we can forget it. So that way there is no problems as such of the information storage in the LSTM network. So this is the expressions through which that each of your computations can be done from your inputs to your hidden, and then the output. And if you see this subscript, say xt-1, that relates that the inputs with the presence with the previous state of information. Similarly, say HT with this HT-1, say BI is the bias unit of your say input gate, F stand for forget gate, and C is a combinations of these which gives you the final output, say let us say the HT state of information. So how we can combine this CNN and the LSTMs in a hybrid network? So the one way to do that you take these informations in a sequential mode, apply these informations to the CNN networks, and then the output of your CNN can be an input to their LSTM, and that way it takes that the exploitations of your these informations is done from the layer by layer, and that will give you that advantage that how our problems can be defined in a better way. So here you see this is your input, then the convolutional layer operation start, there is a pooling, there is a flattening layers, then again there is a dense layers. That is how this LSTM and the CNN define. Now in a combined form, we put in a CNN first and then the LSTMs, and output of the dense layer is actually the same what we have discussed. And these things can be done in a predictions of your geospatial predictions. So let us say that in our problems we see that we have a problem say at a point say latitude and longitude at some point, and we have some variable of say gravity, magnetic, or any other variable. Now our job is to predict that. We develop a CNN LSTM models and predict a variable of any geophysical variable in unknown locations. Unknown locations means we may have that type of examples, that suppose we have a data in some area, we need to predict some variable in a nearby area that may not be in the same. So it is a problem of our predictions. So in that case, what we use that usually, that in the geostatistics, variogram modeling is the one aspect where we do that. There is a given X and the Y, we create that variograms, we create the semi-variograms. So with the best fitting models using the least square base, we can generate that what is the best variograms which explain that explain the distributions of your X and the Y corresponding to the data, and then using the stringing, say one is the interpolation method, we predict it. But other way you can do that, we can combine these things that with the help of the CNN and STMs, and we can devise a framework there, we can handle these predictive models in a better way. So what the flowchart is that let us say that say we take that inputs. It can be your it can be your geophysical inputs, and CNN you apply, and then that output of your CNN can be your inputs to these LSTMs. And once it is the framework is done, then there is a variogram modeling part. This part is saying the variogram modeling, where you will see that we need to generate these variograms with the help of machine learning. So what is happening that we can apply this CNN-LSTM to generate the semi-variogram fitting, and that semi-variogram will be used for your spatial modeling. So what is the advantage is that, so usually what happens that if your number of the data is very small, so in that cases, your semi-variogram fitting models can be unreliable because of the less number of the data. In fact, in our survey data, where we have that, we do not get that much of amount of the data, we cannot collect it in area. So then if the data point is less, then what will happen is that training that AI/ML models it will be a difficult job, because we need that sufficient amount of the data to keep that training, keep some data for the validations and other. So in that cases, how we can use this AI/ML for your particular problem. So it is a problem because this, when you are predicting the geospatial data, it is suffer with the fact that two things. One is that how this data has been spatially changing, whether it is a non-stationary. So these type of problems you have to handle in the same time, whether it is a time varying, time changing non-stationary part is there, and the other complexity parts, noise and other things already we have talked about. So here you see that this is your structure. Here we have what we have done in the flow chart, that we have the data of your gravity, we have the data of your altitude variations in your particular area, and then we have a Bugger gravity anomaly which is aqueous in an area. Then we put the data in a framework, that how we can predict, say, some interface depth. So conventionally what we did, that this 2D radially average power spectrum is a very popular technique to find that how from the data, how the depth of your, say, geological body can be estimated by, say, power law, using the power law or the least squares method. So we have a small area where we experimented it, and now we create the samples with your inputs is your geospatial data with having, say, latitude, longitude, gravity, altitude variations, and what will be your target here will be the interface depth or geological depth, which is actually has been created for your small area. Then using that sampling, we generate the training sample to train these models. And here we have our data processing, our normalizations, scaling, shuffling, to have that there should not be any bias for training and the model development. And we have compared that, say, the LSTMs, CNN, support vector regressions, adaptive neurophagy, Gaussian process, Bayesian neural network, random forest, and see that after that we have also done this robustness analysis, that how your models is robust, means if different level of noise is simulated in your data, how your predictions is actually, how the prediction accuracy in presence of different type of noise. So that gives that some confidence about that how your models can be robust for handling the noisy as well as the noise-free data, or predicting that real world data which obviously have some noise, because in real world we cannot expect that your data can be a noise-free, and they developed a predictive models. And now once it is done, we have applied a real data which has been collected in the other part where this models is not. It is showing that some of the very interesting results in the domains where we, in the main area as well as the area which is surrounding that area where model has been trained. And it actually extracts very beautiful features in a very complex geological terrain. So in order to, before applying these things, we have simulated also that how good our algorithm or the framework in the presence of different type of synthetic model. What we have done that we have created a subsurface models where we are assuming that there are different geological body can be. These are the all rectangular body. This is hypothetical models, and we have placed that the rectangle say 1, 2, 3, 4, 5, 6, 8 number of rectangles. They have their different orientation. They have it is actually we are just perturbed it the different type of models and created that they how their depth is, how their bottom is, what is the density contrast, etc., which is actually required that what type of anomaly we are expecting. So let us say it is a multi-body systems where any type of geological models can be fused it and see how could be your anomalies. Now with that we have applied that the same methodology by doing this power spectral to generate the samples and train this CNN and other machine learning models and compare their results. You see that we can compare that the different depth, different data sets like training, validation, and the testing, it could able to produce a very good image about that how the interface depth is. And if you see this comparison, one-to-one comparisons, the top layer, it is actually the conventional methods where we can get the geological depth. At the bottom, actually the results, which is based on the CNN-LSTM. If you see this one-to-one comparisons of this area in the northeast, there you will see the major structures actually very well captured. In addition to that, there is a loss of information in the periphery of the boundary. That is because once this 2D radially averaged power spectrum has been applied to the data, so there is a squeezing because so you have your observations here, and what will happen in the maximum confidence to estimate the depth actually just below the points where you are computing. Now once you are away from that the particular focus point, though the confidence you are losing. So it is actually squeezing that your actual information. So that is the one drawback in your traditional method, that in the boundary you may not get that coverage. You do not get any information about what is the geological depth. So what we did that we actually formulate these things in the way and we apply that is a real data because this anomaly data and other things are there. So let us say whether we can map these things to fill up that some of the missing information which is there in the periphery of your survey area. It can be extended to the not only the area, it can be extended to the larger area also, this type of methodology. And you see this, the variogram we are talking about, this type of variogram fitting is actually, it is the output of your machine learning, and this variogram fitting we have used that, so there is a theoretical models that is governed by that Gaussian model, can be a Gaussian, can be a spherical, there is exponential. These are the theoretical models of your semi-variogram. Whereas this real data, the variograms is generated is called experimental variogram. We call it a practical variogram. Now our problem is that we are actually, this is a semi-variance curve. So y-axis is your semi-variance, x-axis is the distance between the observations. So here we will see that this how your experimental variogram looks like or explained by the theoretical variogram. So theoretical variograms is a mathematical equations where we need, say, the parameters to express that threat. Now, from the fitting itself, we can have that what type of theoretical models actually best explain that the data distribution in a particular area. Because we are doing this, say, interpolations in many commercial softwares, like you use this GeoSoft, we use Surfer, and many other in MATLAB, Pythons, we do this type of things. But there, what is happening that the standard parameters which is actually inbuilt in the softwares we use it. We never looked into that the underlying process that which type of theoretical model is best described for semi-variogram fitting. Because this semi-variogram fitting is very important to say that the output, that is the contour map, what we generated. Finally we interpret this contour map. Okay, whether it is a any geophysical variable or any, whether it is any estimated variable which is spatially distributed over area. So from that from the image only we actually interpret it, whether it is a fault, whether it is a subduction zones are there, whether any lithological changes are there. So that is actually best described by your how effectively we are predicting that particular variable, or how effectively we are expressing that spatial distributions of your geophysical variable. Please.
I'm not sure, but the way it looks, it sounds like this approach is a substitute to the use of softwares. Like it is an approach that takes over away the softwares. Now my question is based on the cost effectiveness and the time issue. When we use softwares and when we use this approach, which is the best approach when we consider cost and time?
Cost is, you see,
say Surfer and these are the many softwares, they are free. Okay. In terms of cost, say suppose this image has been plotted, one image in GeoSoft. The GeoSoft cost is huge. It is a huge. So cost wise, obviously it is effective. And these things only better way you can handle it, because we have the programs. We can control that what is the seal value, what is the nugget effect, and these are the actually required to describe the theoretical models. So cost wise, obviously it is a cost effective, and the commercial software sometimes it is actually not allowed to see that what is happening inside, because their code is not available or it is not exposed to us. But what is happening, we are actually writing the code, we have the mathematics, so better way you can handle it, that thing, or if any improvement is there, that can be done. Time is in taking only few seconds to run all these programs.
It depends on the ability of a person to do the coding.
if the code is only writing the code is the problem, otherwise it is there, so it is not a matter of the time.
Okay, so in addition to that, we have also computed the uncertainty. What we have stressed about that whatever the predictions is there, we need to also how your predictions limit is bracketed by the variance or the uncertainty. So here you will see that most of our predictions is lying within the uncertainty value, which is acceptable. Acceptable means at least we can define it, okay, that much of uncertainty it is permitted in our data. So this is the study area, what the data we have used in the northeast area. This is geological very complex area. There is a subduction zones. There is a problems with this that basement is very difficult to locate because there are no other data control over this area. There are many data which is acquired by some industry, but it is not accessible. So one way to do that we use this publicly available data from the organizations, or we have some purchase data and do this type of potential field analysis, and we apply this model to the real data of our northeast, and we have divided this whole area and do this power spectral analysis that gives you that this is a very common exercise in the potential field, where x-axis is giving the wave number and y-axis is the power spectrum of your the cell where the data the gravity data has been used, and you see this the power spectrum. This is a plot that gives you that the slope of your each segment has some relations that how the geological depth is, like what is the depth of your geology. So from the formula we calculated that there are different type of interface present in the data. That interface will give you that what is the top structures, what is the bottom structures, what is the intermediate structures, and that is obviously dependent on the wave number, on the frequency. So this type of information has been used the cell by cell in the particular area, and from that we generated the training samples to develop these models. And here we have used that different type of optimizations method in the training, validation and the testing. We have used also the different type of transfer function, that which transfer function gives the best one, because we need to see in your deep learning models that we have to have some combinations of your things, like what is the best optimization method, what is the best transfer function, because all these things are required for your subsequent interpretation. So we have taken one by one approach. So let us say first that we have varied that transfer functions, say LU, tan sigmoid, CELU, sigmoid, softmax, soft sine, soft plus, linear, ReLU. All these functions has been tried, and see that how this training has been with this epoch. And you see this in the ReLU functions is giving the quite good in the three data sets: training, validation, and the test. The red color is showing your the ReLU. And then once it is done, then we have experimented with the optimizations methods also. Here you see in the bottom panel, there it is we have used this stochastic gradient descent, RMS probe, ADA delta, ADA GER, ADA max, and the ADAM. And after once the parameter we have tuned it, we predicted the real data of your northeast, and see this how our predictions is very close to your observations. And then this variogram model has been combined to your CNN-LSTM to see that how our shallow and the deeper interface is predicted by our hybrid network. And left panel is showing that the geological interface depth predicted by your 2D radially average power spectrums. Right panel is showing that the same predictions done by the CNN-LSTM model. You see there is a pictures which is actually the right side panel is better explained by the geology. So there is a thrust belt, there is a fold belt, this is a Kohima basins, who is actually having a large potential of your oil and gas, and there is a different fault systems in that area, and this is actually very important transit. So the different accurate predictions of your interface or geological depth can give you the clear pictures about that, how the subduction takes place, what is the oil prospecting things are there, what is the geological control to explain that particular area. And this has been used for your different interfaces. So you have showing here the deep interface. There you can see that in addition to the main structures, it also gives you the additional features which is actually missed in your conventional mapping techniques. So there is a structure which is beautifully captured by the CNN-LSTM. Uncertainty map has been computed, and see that both the cases for your shallow as well as the deep, and both are giving a very value which is acceptable. And in addition to that, we also gives that our predictions how it is accurate, and from the color bar we can see that how uncertainty has been distributed. And this is the variogram models where we will see that how our the real data of shallow and the deep interface is fitted with these theoretical models like Gaussians, spherical, exponential, with the experimental one. And this is the comparisons that how these models is giving their performance. This is the performance is showing that average accuracy in terms of your mean square error, and there we have seen that the accuracy is actually much more for your CNN-LSTM models. And from the Taylor diagrams, the three data, say standard deviations, predictions, and things. Standard deviation predictions are the correlation coefficient between observed versus predicted can be used to create that Taylor diagrams, where you will see that once the models is superior, they will be close to your perfect one, and their positions can be seen that which one is the best. So these diagrams will allow that many three parameters, if you actually include for creating, then this graph will give you that which models actually the best for your prediction. So this is your comparisons that we have used that the models in that area where these radially average power spectrums, Bayesian neural networks, Gaussian process regressions, adaptive neurophagy inference systems, support vector regressions, random forest, LSTM, CNN, and CNN-LSTM have been compared. Please, George.
Uncertainty, second, two things, like due to the lack of data, training data, which we call it listening uncertainty, and due to the presence of noise in the data, which we call electronic. So the depth model that you shown us here, and the uncertainty map that you have shown us, is it representing both types of uncertainty or just one?
So that is a good question. Because
predictions uncertainty, actually it has been plotted it here. Now the prediction uncertainty is actually, it is characterized by the two things. That uncertainty can be a problems that your data is perturbed by the noise, is number one. Second is that the second part is that how we are emulating the forward response. Means what is the physics behind that? Because the predictions is mapping from your geospatial coordinate to your geological depth, let us say. So in that case, the mapping functions is non-linear or quasi-linear. Okay, so how our this neural networks or CNN-LSTM actually compute this or emulate this underlying mapping, that also another source of your uncertainty. So it is actually combinations of both the things. So we have not separated it so far, because there is a not clarity about that when these things actually there. So we need to pay attention in that, whether we can separate it out by some mathematical techniques, that this is the uncertainty about that, this is that. So one way you can do that, say we can simulate the different type of noise. So one part you fix it and you just explain the rest of the part. So in the Bayesians, what is happening that these type of things actually can be actually better handled, because in the theory that hyperparameter is there. That hyperparameter value, actually it is tuned to the two things. One is that one parameter is related to the noise variance in the data, and another parameter, it is related to the complexity in the model. What we call this, that related to the forward modeling or the forward response, how accurately we are mapping it. So from the re-estimation process, evidence-based maximization process, we can look at the value, the estimated value. From that, we can have some idea that which part is actually dominated. But you want that the total distributions of these two parts in a particular panel, that we look into in future, that how it can be done. Good. So this is the uncertainty. There you will see that this how these predictive models is consistent over the particular area, and you see most of our uncertainty is following similar, and there are some features, and that will give you that particular things, because you see there are 8 models has been compared, so they have been learned in a different way. Although these other parameters, the training sample, number of the data during the training, validation, testing, we kept it same to say that competition should be very fair among this machine learning model. So this is one example where we have seen and compare it, and we have some time of 5 minutes. So let us say that we'll briefly just go through that autoencoder, which is already discussed it, and it has a large number of applications. Usually we have done that. One example is that principal component analysis. So we did that in many cases, that say let us say in a classification problems, where by looking at the data, by plotting the data, say 3D, it is very difficult to separate some of the features from visualization. Okay, we may increase the dimensions to see that if some of the features can be linearly separable or no. So the principal component analysis, basically it is a linear transformation of projection system, which actually allow you the original data to transform to a new projection systems, and with keeping the variance, which is permissible, and that will allow that classification problems can be simpler, and we do not have the problems about the storage of that one. So the autoencoder, which is actually there, the basic structure is the input and the output is the same, and it is actually very if you use the transfer functions is linear, so this autoencoder can act as that PCA job. Okay, so in addition to that, the PCA is actually normally it is a linear projection system. Although we can define this projection system in the nonlinear way, but it has been defined originally as a linear projection system. But in the autoencoder, there is a flexibility that we can use this nonlinear transfer function, so that can handle both the things. This is the one very very key advantage of this autoencoder. So there is a variance of your autoencoder, like say variational autoencoder. They use that Bayesian statistics to train and predict these things. So what is happening that they take that the mean, mode, and variance of your statistics, and that we try to map it between the input and the target. So this is the structures where encoder is there. Encoder will actually compress the input informations, and then the decoder will use again this express it. So this is a part which is hidden to that, and whatever the input image is there, it will actually reconstruct it. So this is the process which has been used. The variable has been described in the latent space, and the theory is that this loss function minimization. So loss function minimization can be done. Either you can define at the L1 norms or L2 norms, like mean square errors or mean absolute errors. There are optimizations method which has been used, backpropagations with the gradient descents, and there are varieties of the autoencoder as there. Basic autoencoder, sparse autoencoder, denoising autoencoders, variational autoencoder that uses this Bayesian statistics or the probability theory, and the basic convolutional autoencoder. So there is a variety of these things, and new models, hybrid things are coming in this domain, and it has been used, say basic autoencoder for your feature compressions, sparse autoencoder for sparse signal detections, denoising autoencoder for noise reductions, convolutional autoencoder, say seismic phases classifications, variational autoencoder. Variational autoencoder actually it is basically uses that Bayesian theory what we have used in there is a prior state of information, there is a posteriors, there is a likelihood, and they basically has that concept that the statistics, mainly the statistical inference has been used in your variational autoencoder framework. So this has been used in the different domains, from your remote sensing to image processing, geochemical anomaly detection to seismic data processing, geological models, oil log analysis. There are varieties of applications is there with this autoencoder. Obviously, every models has some advantage and the disadvantage. The basic disadvantage, obviously, we have that overfitting. That overfitting is a very inherent phenomenon of neural network modeling, because whatever the things are there, you are providing input to the target and provided the ample time and the space, and we are using the back propagations. So it will iterate it because your target is fixed. So ultimately this theory allow you to actually minimize the error function, but the disadvantage is that the basic node is the neurons, so it has the problem that it memorizes these things. So that is a very critical issue in all type of machine learnings, particularly the neural networks has been used. We have to be careful about that, when we should stop it or how we can prevent it, the overfitting. Because ultimately once it is overfitted, then it will give very excellent performance in your training data, but it may provide adverse results in your new data, which is very unknown to the network. And last, we will conclude that there is a adversarial networks. So we have that clear distinction about what is discriminating AI and what is generative AI. In the discriminating AI, we have that, say, the way we have learned about, say supervised type of networks. We have a training data, that means it is a labeled one. We have an input, we label it, it is a corresponding to a particular type, say we are denoted by, say, 1 0 0 1, something like that. And this training type of data we apply to a neural networks models, say discriminating models. And once it is trained, it know that what is the input and what is the target. Then the next step is we apply a new data, it will predict it. And these predictions will give you that the probability, at what probability is to have that particular type of present. This is what about your discriminating AI. The generative AI or GAN, this is the basic things, that here we have the training data and we have the generative models. So with this sampling, we generate the sample. That means we are creating that observations, basically what type of things are there, provided follow some hypothesis. That hypothesis is obviously driven by that it is not very fully supervised. It can be innovated in an unsupervised way also. That is the main challenges in the that is the main advantage in the generative AI. Initially thought that we generate the data, that should be follow some hypothesis. Okay, but now the new experiment is coming that generative AI is thinking it is own. So that is what our Hinton's reported in some of the examples, that he actually learning from his own. Earlier, this AI, we thought that we need to provide some examples, otherwise it will fail it adversely. But now things are that now it is like that. It is there, but some new things also it is start learning from their own. That is the main advantage of the generative AI, and so it has that real and the noisy data, and both the things can be provided, that there is a generator and there is a discriminator. So both the things actually learn simultaneously, and this will give you the flexibility, as we discussed about that advantage about that robustness in the generative adversarial network. So there are as many number of the varieties of the GAN has been come. There is a cycle GAN, there is a mu GAN, there is a different type of architecture has come, and it has been used in a different types of problems. So that is what all about that exposure of your